Welcome to another edition of the screencast for multivariable calculus. Here we're going to do a quick example using Lagrange multipliers. In fact, this is a pretty popular problem. You'll find it in pretty much every calculus textbook. It involves the so-called Cobb-Douglas production function from microeconomics. By investing X units of labor and Y units of capital, a low-end watch manufacturer can produce 50 times X to the 0.4 times Y to the 0.6 watches. Find the maximum number of watches that can be produced on a budget of $20,000 if labor costs $100 per unit, capital costs $200 per unit. Classical Cobb-Douglas question. I do like the little bit of shade thrown in there about low-end watch manufacturers. This is a fictional company. We don't need to be judgmental about them. Anyway, it's pretty laid out pretty clearly what we're trying to optimize. The production, of course, and we have an explicit formula for it, and the variables even laid out for us. So we'll make f equal to that 50 times xy. I made the exponents fractions here, and you might notice that their sum is 1. And that's not a coincidence. That happens in a lot of these models, and it's for a pretty simple reason. Mathematicians would call this a homogeneous function of degree 1. But what it means is if we were to, say, multiply our investment, and say we triple both labor and capital, we should expect production to triple. That's exactly what happens. If we plug into the formula 3x and 3y for our inputs, look what happens to that 3 when we pull it out. Those exponents add, of course, there, and if they're rigged to add to 1, we get exactly 3 to the 1, or 3 times the whole output. So we've got our function to be optimized, or maximized in this case. What's left is the constraint, and of course that will come from the budget. I've got $20,000 to spend on labor and capital, and of course we're going to want to spend all of it if we want to maximize production. So we will make our constraint, and we'll introduce this function g, right, the budget function here, and it's a simple linear function, 100 times the units of labor and 200 times the units of capital, and we set that equal to $20,000. So this is going to be a level curve now of this function g, and we know from our theorem that the maximum local extrema for f constrained to this g will happen where their gradients line up. So we just set up the equation. Gradient of f is lambda times gradient g, where lambda is some unknown scalar. So we need to compute the gradient, and we go through it, find our partial derivatives with respect to x, simply the power rule. So you see that the 2/5 comes out, and the exponent gets reduced to minus 3/5. Right? And again, you can kind of see these opposite sign exponents there. That's not a coincidence either. For y, similar story, got 3/5 here, and the right-hand side is fairly trivial. Lambda times 100, 200. I have a constant gradient for a linear function. There. Now you've got lots, well actually let's neaten up these coefficients a little bit first. We got 20 and 30 there. And you've got lots of choices on how to go about solving this guy. Common is to solve for lambda in each equation and set those equal to each other. But I'm actually going to take a bit of a shortcut here because I'm going to observe a few things. X and Y, of course, are not 0. We're not interested in no production here. We know they're going to want to be positive. So that allows me to go ahead and take ratios. I can divide both sides of these two equations up here. So we're going to divide the y partial derivative by the x, and the same corresponding on the right. The right simplifies quite easily. The lambdas drop out. That is a nice feature here. We don't really care about its value. And then on the left, these exponents, if you work them out, come very nicely in the ratio form. We got 2/5 minus a minus 3/5. We just get 1 each with x on the top and y on the bottom. So this ratio x to y, it turns out, is just a constant 4/3 in this case. Or rather, y is 3/4 x. So what's left to do? We have our constraint still to satisfy. We just have a relation on y to x. So we plug that into g. Right? X is x. Y has to be 3/4 of the size of x to maximize our production. So we just figure out what that budget allows by plugging in, and now it's very simple high school algebra, or maybe middle school algebra. Even x is 80, y is 3/4 of that, so we get 60. And all that's left to do to find out what that maximum production is to plug back into the function f of 80, 60, which I believe is around 3,300 or so. And we'll check that with good old Mathematica here, including a nice picture of what's going on. What we see here is the constraint line, the budget line, which is simply literally a line. The sum has to be to 20,000 here, and behind here, the colorful graph, are the level curves of the Cobb-Douglas function here. And of course, the point that we're interested in, right, happens right around here, right, where it's where the gradients line up, or another way of saying the gradients line up, or that these curves are tangent, or mutually tangent at that point. 80, 60, we'll just confirm what that value is. 50, 80 to the power 4, 60 to the 0.6, indeed, around 3,300 units of low-end watches.